Does the top quark decay before it gets affected by color confinement? And thus, can a bare top quark be observed? In general, can bare quarks be observed above the Hagedorn temperature? Okay, we have a number of concepts over here that we have to speak about. One is the Hagedorn temperature. So, what is this Hagedorn temperature? So the Hagedorn temperature is a theoretical temperature limit in particle physics in the context of what we call hadronic matter. What is hadronic matter? Hadronic matter is your standard matter that you are aware of, matter that is made of quarks. So protons and neutrons are made of quarks. Electrons aren't made of quarks. Okay, electrons aren't hadrons, they're leptons. But the universe that we know, the world that we know, is all hadronic matter. And the Hagedorn temperature is a theoretical temperature limit in the context of hadronic matter. So at this temperature, the Hagedorn temperature, if you add more energy to a system of particles, like let's say you have a particle accelerator, or you have the early universe, and you add more energy to a system of particles at this temperature, then this doesn't increase the temperature. It instead produces more particles. Okay. So the idea is that at very high temperatures, the energy density is so high that it continuously converts into the creation of new particles. So the Hagedorn temperature is a theoretical upper limit on the temperature of matter, beyond which our current understanding of particle physics breaks down. And this is essentially represents a phase transition between different phases of matter, like between water and ice or water and steam. These are different phases of water, right? Similarly, the Hagedorn temperature represents a phase transition temperature, and it's about 1.75 trillion Kelvin, 1.7 times 10 raised to 12 Kelvin. That's the Hagedorn temperature. That is what it is. Now we're talking about bare quarks, right? So at temperatures above the Hagedorn temperature, there will be a phase transition and there will be a different state of matter that will exist. And that phase of matter, state of matter, is called a quark gluon plasma. In a quark gluon plasma, quarks and gluons are deconfined and they can move freely. It's a soup of quarks and gluons. Gluons are force carriers, so to say. Okay, so they will all intermingle, they will be deconfined, and they'll move around freely. It will be quark gluon soup, quark gluon plasma. And this state of matter could potentially allow for the observation of what you call bare quarks. Okay, now what is color confinement? That's another term that we are using over here, color confinement. So color confinement states that quarks cannot be isolated singularly. Quarks can only be found in bound states called hadrons. Okay, so there are six quarks: up, down, top, bottom, strange, charm, and these are the fundamental building blocks of the of hadronic matter. So confinement says that you cannot have isolated quarks. Quarks are always found in bound states called hadrons. Now there is something called color charge. Okay, and think of it as a quantum property. It's not really a charge, and it's not really colors like red, green, and blue. Even though quarks carry what we call one of the three color charges, red, green, and blue, but this color charge is actually a kind of quantum property. So quarks carry one of three color charges: red, green, blue, and anti-quarks carry anti-colors: anti-red, red, anti-green, anti-blue. And there is a property called color neutrality. So hadrons, bound states of quarks, are always color neutral. So this can be achieved by either combining three quarks with different colors into baryons. Okay, protons and neutrons are baryons, and they are made of three quarks. Or you can combine a quark and an anti-quark with corresponding color and anti-color charge, which are mesons, pions, kaons, etc. Okay, so that's how you achieve color neutrality. So similar to how atoms are electrically neutral because they have equal numbers of protons and electrons, similarly hadrons are color neutral because their quark colors combine to cancel each other out. Now there is a strong force involved in quark interactions, and the strong force between quarks increases with distance. Okay, in electromagnetism, in the gravitational force, when objects or two bodies move away from each other, the force decreases with distance, right? With increasing distance, the force decreases 1 upon r. But in quarks, the strong force between quarks increases with difference. So imagine two quarks that are connected by a rubber band, a flux tube. So if you pull them apart, you're going to have to, impart a tremendous amount of energy. And as you pull them apart, the tension in this band, this rubber band that connects the two quarks, increases until the band snaps. And when the band snaps, it creates two new ends. And this snapping essentially represents the creation of a new quark antiquark pair. This leads to the formation of two new hadrons instead of isolating two single quarks. So that's essentially what it is. Okay, that is color confinement and all that. Now, above the Hagedorn temperature, the concept of confinement, color confinement, no longer applies, and the thermal energy is sufficient to overcome the strong force. The thermal energy of the temperature is sufficient to overcome the strong force that confines quarks within hadrons. And that's how you have the formation of the quark gluon plasma, where quarks and gluons freely move around over large distances. And this state of matter is believed to have existed just after the Big Bang. Now you are mentioning the top quark. It is the heaviest of the quarks. It is an extremely massive quark. It's unique among all the quarks because it is tremendously massive. It decays extremely quickly, and it decays faster than the time it would take for color confinement, which is the process that binds quarks together to form hadrons. Okay, so top quarks are unique, such that in such a way that it is possible to observe an unconfined bare top quark in experiments. And that is about it.